I will talk about the nonlinear asymptotic mean value properties for Monge-Ampère. And this is a joint work with, I have to mention my collaborators, of course, with Pablo Blanc, who is in Jyväskylä University in Finland, Fernando Charro from Detroit, and Juan Manfredi from Pittsburgh, Detroit and Pittsburgh, of course, in the US. Okay, what is the meaning of a mean value property? I have to make a short introduction saying something of what is the classical sense of a mean value property. Then I will introduce some asymptotic mean value properties, and I will explain why the term asymptotic is there. And later on, I will say something about the Monge-Ampère equations. I will give you the precise statements, but I will not give you the full details of the proof. I will only sketch the easy case. So you can have a sort of glimpse of what's going on with the proofs, but recall that this is only the sketch of the easy case. Okay, let us start with the most classical mean value property that is for the Laplacian. For the harmonic function, in a Rn, in a smooth domain in a Rn, in a ball in a Rn, you have the mean value property that says that u is harmonic inside the domain if and only if the value of u at some point x is exactly the mean value of u in the sphere of any radius, of radius r, around the point x. Or the second possibility is the mean value in the solid ball around the point x. Yeah, if you have questions or comments or whatever you want, or something that is unclear, please interrupt me at any time without hesitation. So say, Julio, stop, and I will try to answer. Okay, so this is the mean value property for harmonic equations, for harmonic functions. And you can also write it in this other way, that it is the asymptotic mean value formula that we were talking about. And that says that, of course, u of x is equal to the mean value in the sphere of the values of u, but you can divide by 1 over r squared and take the limit as r goes to 0. And if this limit, as the sphere shrinks, goes to 0, then the function is harmonic. And this is if and only if. And the same happens with the mean inside the ball. If you take the mean value inside the ball and you subtract the value of u at the center of the ball, when you divide by r squared and you take the limit as r goes to 0, then you also get 0. So these two properties in the limit are weaker than the mean value for every radius, of course, because if this difference is 0 for every radius, as it happens, then the limit is also 0. But then to have the limit, to have the asymptotic mean value, it is enough to recover harmonicity. So you only need a local property close to the point because the ball is shrinking around the point, and you will also recover the harmonicity. Okay, this is more than that. In this sense of asymptotic mean value properties, so in these limits, you can also characterize super and sub-solutions. So if you take a function, the function is subharmonic, so it has an inequality, the Laplacian of u is bigger or equal than 0, if and only if the lim sub is bigger or equal than 0. And here the epsilon, I will take to epsilon for the rest of the talk for the parameter that controls the radius of the ball that we are shrinking around the point. And there is a converse, or a sort of, not a converse, a different statement. Here is the mean value with the sphere, and there is also a mean value with the solid ball, asymptotic mean value with the solid ball with an inequality that characterizes being subharmonic. And of course, the reverse inequality gives you superharmonic function. So if instead of lim sub, you put lim inf less or equal than 0, then you get the Laplacian is less or equal than 0 inside your domain. And this holds for every x. This inequality needs to hold for every x inside your domain, and you get a subharmonic function inside your domain. Okay. What about the discrete versions of this thing? There are also discrete versions of this thing that says, okay, if you take an orthonormal basis, the canonical basis of Rn, and you move epsilon to the left, epsilon to the right, epsilon up or epsilon down, and you take the mean of these four movements, of the 4 points in R2, then use harmonic if and only if u at some point is the mean value of these 4 points plus a small error, a little o of epsilon squared. And I will keep this notation of little o of epsilon squared for a quantity that when you divide by epsilon squared and take the limit as epsilon goes to zero faster than epsilon squared. So this is the meaning of the little o of epsilon squared, and it's the same thing as saying that when you divide by epsilon squared, the limit is zero. So when you subtract u of x minus the mean, this discrete mean, and you divide by epsilon squared, this quotient goes to zero. Okay, what about operators that are not the Laplacian but are linear? You can also do that if you add coefficients, aij, to your second order linear operator. This is not in divergence form, but this is linear. And if you add coefficients, you can also obtain mean value formulas. The mean value formulas now depends on x. And instead of taking the mean in the ball, in the rounded ball of radius epsilon around the point, you take the mean in an ellipsoid that is deformed and oriented according to the eigenvalues and eigenvectors of the matrix aij. And as long as the matrix aij is uniformly elliptic, you will get the same kind of formulas that we described here. But instead of integrating in the solid ball, you need to integrate in an ellipsoid deformed by the matrix aij. Okay, now things can get a little more involved, and we can talk about mean value formulas, but for nonlinear operators. Take, for example, I select this example. This example is the normalized P Laplacian, which is the gradient u to the 2 minus p, the divergence of gradient u, p minus 2 gradient u. This is the usual P Laplacian, but now we are normalizing it. So this operator is one homogeneous. And this is a combination between the Laplacian, the usual Laplacian, and the infinity Laplacian, also normalized. Okay, when you have an equation like this equal to zero, this is nonlinear because this part of the equation is nonlinear. And here you can see that you have powers everywhere. So this is a nonlinear operator. This is a nonlinear second order operator. It is elliptic, but this is nonlinear. Okay, for p between 1 and infinity, we also have a nonlinear mean value formula that characterizes viscosity solutions. So when you take u of x is a mean value of u in the ball of radius epsilon. This is the usual mean in the solid ball of radius epsilon. But here you have a max mean in the ball of radius epsilon. You have something like, I don't know, the median values, or, well, the intermediate value. This is the mean value between the maximum of the ball in the ball and the minimum of u in the ball. And the little o of epsilon squared means the same as before. When you subtract and you divide everything by epsilon squared and you take the limit, everything goes to zero. So u at some point x is almost this mean value in the ball of radius epsilon plus a small error that goes to zero faster than epsilon squared. So you can recover second derivative. And in some sense here and there, you have hidden the second derivative of your function. Okay, everything depends on p because the formula that you have here depends on p, and you have this 1 over p minus 2 there. But everything, the coefficients that you have depends on p. And that's it. This is an example of an asymptotic mean value formula that characterizes also viscosity solutions to a nonlinear PDE. So for nonlinear PDEs, you will not expect a mean value formula that holds for every possible ball. You need something that shrinks around the point, and you need a small error So this is why asymptotic mean value formulas are needed here. But the key fact is that this characterizes the solution. So U is a solution if and only if U verifies this formula. Okay, now about Monge-Ampère equations, and now we are entering into the core of the talk of what are our results for this kind of equation. So take the Monge-Ampère equation. What is the Monge-Ampère equation? Is you take the Hessian of the function U. So you take the matrix of all the second derivatives. This is an n times n symmetric, real symmetric matrix of n times n in Rn. And you compute the determinant of this matrix. And you prescribe, your equation prescribes that this is equal to F. Okay, take a convex domain omega, say that omega is the ball of radius 1, and assume that you have a solution to this equation, to the determinant of d2u equals to F. In order for the operator, for the determinant of d2u to be elliptic, you need to impose something, and the something that you need to impose is that the Hessian is non-negative. So we are talking about convex functions here, because if the Hessian is a non-negative matrix, then your function looks like this. It has a positive, or there is a non-negative second derivative in every possible direction, and your function will be convex. So we are going to fix ourselves in the setting of convex solutions to the Monge-Ampère equations, and this imposes that F, the right-hand side, is bigger or equal than 0, so not negative, and your solution U, your functions U that are involved here are going to be convex functions. In terms of the eigenvalues of the Hessian, as I told you, the determinant is the product of the eigenvalues, and convexity is saying that the minimum of all the eigenvalues of d2u is bigger or equal than 0. So every possible second derivative of u in any possible direction is bigger or equal than 0. So your function look like this, look like a smile in every possible direction. So it is convex at the end. Okay, this is the equation that we are going to talk about. And our first result says the following. Take a function, phi of epsilon, that verifies the following thing. So phi goes to plus infinity when epsilon goes to 0, but when you multiply by epsilon, it goes to 0. So it goes to plus infinity at the origin, but not too fast. It has to be slow enough so that when you multiply by epsilon, it goes to 0. So any function that verifies these two properties will do the job for you. If you want to choose one and fix one for the rest of the talk, you can take phi of epsilon equals to epsilon to the minus 1/2. So this is, if you want, we can stick to this particular choice of phi. Okay, now take a C2 function. Assume that U is convex and smooth enough. So C2. Fix a point inside omega, and we have the following asymptotic expansion of your function U. So U of x minus a mean value of U deformed by a matrix A in the ball of radius epsilon. This is, I will say something more in the next slide, but this is the mean of U in some ellipsoid that is the ball of radius epsilon deformed by the matrix A and centered at the point X. And you take the set of matrices that are involved in the infimum as matrices with determinant equal to 1, and that has all the eigenvalues less or equal than phi of epsilon. So the matrix as a symmetric positive definite matrix has to be less or equal than phi epsilon times the identity. And this is where the function phi that verifies these conditions enters into play in this mean value stuff. So U minus this thing, this infimum, this mean value of this nonlinear infimum of the values of U around the ball is like the determinant of d2u. This is what you want, to some power, times epsilon squared plus a little error. And the little error is, as before, a little of epsilon squared. And you have this funny constant n over 2n plus 2 in front, but this is just, let me say, a technical stuff that has to appear some constant that depends only on the dimension in front of this. Okay, two remarks. The first remark is that when you take a matrix with determinant equal to 1 and you take this integral, this mean value in the bolus radius epsilon of the values of u at x plus the matrix times y, this is the same as the mean value of the values of u, but in an ellipsoid, because you change variables exactly. This is the change of variable theorem, and the determinant of a equals to 1 implies that the Jacobian that you have to put here is equal to 1. So you don't care about the Jacobian, but you change the set. And the set, this ellipsoid is exactly like this. You take the ball of radius epsilon around 0, you deform it. You take the round ball, you deform it by the matrix A, so you shrink in some directions, you enlarge it in another directions, and you can rotate it as well. And now you place this rotated ellipsoid centered at the point X. And you take the mean of u in these ellipsoids. Okay, the second, those are the mean values that enters into this infimum here. Okay, the second remark says that when you take the restriction that the matrix is less or equal than phi epsilon, this makes everything local. Why is that? Because when you take the distance from the ellipsoids to the center, to the point X where you're taking these averages, then the distance is less or equal than the matrix times y. Y is in the bolus radius epsilon. The matrix is less or equal than phi of epsilon, so you get epsilon phi of epsilon, and remember that the condition says that epsilon phi of epsilon goes to 0. So epsilon goes to plus infinity at 0, but not too fast. So this can make this means values local. You localize the mean value around the point X. Okay, now the following question is, can you do a similar expansion without localizing things? And the answer is yes, but you have to ask, of course, the ellipsoids to be contained in the set in omega. Omega is the set where your function is defined. So you have a function u that is convex and C2 in omega inside the set, and you have that u at the point X minus this infimum, and in this infimum you are not restricting the ellipsoids to shrink around the point, but you are restricting all possible ellipsoids that can be very narrow in one direction and very long in the other. So, but they have to be contained in omega, so you have this this evaluation of u at this point is well defined, because u is defined only in principle only inside omega, and is C2 only inside omega, inside your domain. So this plus the same constant, the same determinant with the same power epsilon square is again a little of epsilon square. So you have a asymptotic expansion in terms of a mean value of u around some ellipsoids close to the point X in the previous slide. And here you have some mean value with some ellipsoids that are only contained in omega. That involves, or that is related with the determinant of D2U with the equation with the Monge-Ampère operator that you want to solve, plus a little of epsilon square. And this is the key point, the key formula to obtain something. Okay, what is the something that we can obtain? The first one is that a characterization for C2 solutions. If you have a solution that is smooth, solution to the Monge-Ampère equation, this is if and only if, so the following are equivalent. This is if and only if you have a solution to the Monge-Ampère equation, if and only if u of x minus the mean value, this mean value is f of x to some power with some multiplicative constant times epsilon square plus a little o of epsilon square with a small error. And the same happens with ellipsoids that concentrates near the point X, or with ellipsoids that are only contained in omega. So any of the three statements implies the other two. And you have a characterization of being let me say, Monge-Amperistic equation or Monge-Amperistic function. So a solution to Monge-Ampère, a classical solution to Monge-Ampère in terms of a mean value property that involves ellipsoids that are close to the point, or that involves ellipsoids that are only contained in the set where your equation is verified, or where your function lives. Okay, can you go one step further?
May I just ask a quick question? So this
Sure.
this O of epsilon squared, does it need to be uniform in no?
No, in general, it's not going to be uniform. So for every point x, you will have a different little law of epsilon square, and that's life. You say no, but no. This error term is just a little law of epsilon square for each point x inside omega, but it's not uniform in general. For the Laplacian, where is the Laplacian? Here. For the Laplacian, it is uniform.
It is zero, yeah.
It is zero, but it is uniform for, let me say, this second order, as long as your function is more regular than C2. It is C3, for example, you can add a little o, not a little o, a big O of epsilon to the power third, to the cube. And this is going to be uniform as long as the third derivatives of your functions are bounded. But here, it is only a C2 solution that is enough to define the operator.
Thank you.
Okay. No, please. Any more questions, comments, something? No? Okay, I will continue then with the characterization for viscosity solutions. In viscosity solutions, in the viscosity world, we are asking only for the solution to be continuous, and being a solution to the equation or a solution to the inequality here is that when you touch u from above or from below with a paraboloid, with a convex paraboloid, because we are talking about convex functions, then the inequality holds for the paraboloid. And the paraboloid is a function that is C2, so we can apply, or we can use our previous stuff of saying this asymptotic mean value formula, but with inequalities only. So this is also, as happens for the Laplacian, this also holds for super and sub-solutions. So U is a viscosity subsolution of the equation, so it verifies that the determinant of D2U is bigger or equal than F in the viscosity sense, so touching from above with convex paraboloids, if and only if the U of x is less or equal than the mean value, this strange mean value among all possible ellipsoids that concentrates near the point, plus this epsilon square term that involves the right-hand side f, and a little law of epsilon square, and also is less or equal than the mean value when the ellipsoids are not shrinking around the point x, but only contained in omega. Okay, so this is a characterization of what is a viscosity solution to the Monge-Ampère equation in terms of nonlinear mean value properties for your function u. Always in the viscosity sense. If you have a C2 solution, if your solution happens to be smooth enough, then you have a characterization using u. You don't have to touch u from above or from below with a paraboloid. You can use the same function u inside, and this holds, this equivalence holds. But if your solution to Monge-Ampère is not smooth enough, it's only a viscosity solution, you also have an interpretation or a characterization in terms of mean value properties. Okay, you also have a discrete version, as happens for the Laplacian for these mean value formulas, and the discrete version says as follows. You take your function u at a point x is the infimum for every possible orthonormal basis. So you choose the directions, you choose an orthonormal basis, you choose directions, and you choose multiples, alpha, You choose coefficients alpha in such a way that the product of all these coefficients alpha 1, alpha n is equal to 1. There you see something like the eigenvalues of the matrix, and here you see something like, it's like the determinant of the matrix A to be equal to 1. You impose the same restriction as before, that the eigenvalues, or sort of eigenvalues of the matrix, have to be less or equal than phi square of epsilon this time, but this is a technicality. And you compute this mean. This means, so you take in the direction, you make movements in the direction of the vectors Vj of size the square root of alpha I, one step to the front and one step to the back in the direction of Vj. You take the average of all these movements. This is the discrete mean value property for u of x that gives you again the determinant of d2u plus a little o of epsilon square. And again, the little o of epsilon square is not uniform. It's exactly as before, but now the mean value, or the mean that is involved, is discrete. And this is going very helpful at the end of the talk when we talk about a game for Monge-Ampère. Okay, you have also a characterization of viscosity solution, of C2 solution, and of viscosity solution. When you have the equation, when you have the determinant of d2u equals to f, you replace the determinant by f in the asymptotic mean value formula that you have before, and what you get is the asymptotic mean value characterization of your solutions, of your equation. And of course, also holds in the viscosity sense, everything in the viscosity sense. You have a C2 version of this statement, and also a viscosity version that is this one. Okay, what are the key ingredients that enters into the proof? Now I am going to enter into the proof, and I am going to be very quick saying something about the proof of the result, but I'm going to show you the key ingredient and where they are used. Okay, the first one is a simple linear algebra. Well, it is a linear algebra identity that says that the determinant of a matrix, you take a negative matrix, this is going to be your Hessian in the calculations. So the determinant of the matrix is the infimum among matrices of determinant 1 of the trace of A transpose MA. You take the trace of this combination, of this multiplication from the left and from the right of the matrix M by A. You consider the trace of this, you take the infimum among all possible matrices of determinant equal to 1, and you obtain the determinant of M. To the 1 over n, and this the little n that appears in front is part of the funny constant that I show you that appears in front of f in the mean value formula. So it is part of this n over 2n plus 2, this little n that is in the numerator of the fraction. This n is exactly this little n that appears here. Okay, now for linear averages, if you take this quadratic polynomial, let me say you take the matrix, you multiply by y, you multiply by y again, this is a quadratic term, and you integrate this quadratic paraboloid centered at the origin in the ball of radius 1, in the ball of radius epsilon, then you get something that divided by epsilon squared, it is the same size. This is quadratic, so this is epsilon squared. The mean value in the ball of radius epsilon. This n plus 2 is exactly the n plus 2 that you have in the denominator, and this gives you the trace of the matrix M. So, and this is just a explicit computation. This is calculus in several variables computations. This is what I am teaching to my students right now in this semester. Okay, what is the proof? The proof of the result of the asymptotic. I'm going to show you the proof of the asymptotic mean value property in the C2 case, so for smooth functions, and when the matrix is strictly positive. So you have that the Hessian is strictly positive. All the eigenvalues are strictly positive at the point x. When one of the eigenvalues is equal to 0, so remember that the Hessian has to be positive semi-definite, so the function is convex, but it's not strictly convex in general. When it's strictly convex, this is the easy part of the proof, When it's not strictly convex, you need some extra work. You need some extra details. It is not difficult. It is not that terrible, but you need something extra. Okay, so you take the second order Taylor expansion of U around the point X. Recall that U is C2, so you have everything is well defined. U of X, the gradient of U times Z minus X, and now you have the Hessian and the quadratic term with 1/2. And since the function is C2, you have that U minus this paraboloid, the second order Taylor expansion of your function U is a little O of what is left. So U of X, U at some point, U of Z is between two paraboloids, the second order Taylor expansion modified by a small eta times Z minus X squared, or with a plus or with a minus. With a minus, you have it from below. With a plus, you have it from above. Now, call these modified paraboloids as P plus or minus, and the plus or minus is according that you add or subtract the term in the expansion, and take the mean. If you compute the mean in the bolus radius epsilon, that P plus or minus at X plus AY, and you subtract U of X, then what you get? U of X cancels the first term in the expansion. So this is out of business. The second one is linear, and when you compute the mean of a linear function centered at X at this ball, then this also cancels because this is even. And it only remains the second order part. The second order part is given by this term that you can rewrite it in this way. And when you rewrite it in this way, you figure it out that this is exactly the trace of a matrix times A transpose. So you multiply by A on both sides of the matrix times Y and Y. So here we are using our second property, that is the linear average of a matrix computed at YY is the trace of the matrix, but now we have the trace of this D2U plus or minus eta multiplied by A and by A transpose. And now you use the first identity that says that when you compute the trace and you take the infimum among all possible matrices on both sides of this identity, then you obtain the determinant. So if you take the infimum here, and here there is a trick that you compute with matrices that are less or equal than phi of epsilon, but this is not going to be a real restriction because the matrix in which this infimum is achieved, this infimum is going to be achieved when the matrix is positive definite. The infimum in which this infimum is achieved has fixed eigenvalues, so it's going to verify this restriction for epsilon small enough. So when you compute the infimum among all possible matrices on both sides of the identity, and you use this property of the determinant, you obtain the determinant of D2U plus or minus eta. Now you don't want to compute it and the paraboloids. The paraboloids are the second order Taylor expansions of your function U modified by this little eta. But you want to compute it in U. You want to compute the infimum among all possible matrices at the function U, not the function P or plus or P minus, but you use that U is between P plus and P minus to obtain an inequality from above or from below with a plus or with a minus. And now you end up saying that, okay, what I have here does not depend on eta, and what depends on eta here goes to the right determinant of D2U 1 over n, so converges as eta goes to 0 to the exact quantity that you want. So at the end, you take the limit as eta goes to 0. And that is the proof of the results for the C2 case, for U C2, so smooth enough so you can make Taylor expansions. And you can obtain the little o of epsilon squared, the error term. You can control it from above or from below with this eta, and at the end you take the limit as eta goes to 0. That is the proof. And you use these two key properties in red. So you use that you have a formula for the determinant in terms of traces, and you also use that mean values of, let me say, quadratic terms inside the ball of radius epsilon gives you the trace of the matrix M that is involved. So these mean values are related to the trace of M, and the trace of M, when you compute the infimum, gives you the determinant of your function. And this is the core of the proof of what is going on, what happens. Okay, now I'm going to comment briefly on a game. Let me say this is a probabilistic interpretation of Monge-Ampère operator in terms of a game that has only one player. So instead of a game between two players, you have only one player, and you can think about the game of a control problem. So you have one person, one controller that want to control what's going on. Okay, so what are the rules of the game? How do I move inside my domain omega? I will move inside this box, this square of this rectangle that is my screen. This is going to be my convex domain omega in Rn. I will fix this screen to move around. Okay, I have a final payoff outside the screen. So when I exit the screen, something is going to happen and is related to this function g. And a running payoff that is inside the screen, that is a continuous function that gives me some values inside. I fix a small epsilon. I start with an initial position here at some x naught. And at each point, at each movement, I choose an orthonormal basis. So I choose two vectors, orthonormal basis like this. And the next position is going to be given by a multiple in the direction of this vi of size epsilon times some quantity that I can also choose between some coefficients that has product equal to 1. The product of all these coefficients has to be equal to 1 and has phi less than 1 over epsilon. It cannot be terribly big in here. So you make all these possible movements. So I move, let me say, in the horizontal direction, something that is small, but I can enlarge the vertical direction, or I can do the opposite. I can restrict my vertical direction and enlarge the horizontal direction as I want, and I can also rotate these two vectors. Okay, all these possible positions, that is, I can go up, down, to the left or to the right, some amount that is given by this epsilon, the square root of alpha I, all these possible movements have the same probability. So I toss a coin, 1 over 2n coin, and then I choose one of the, in this screen, one of the 4 probabilities according to the thing. And at every point that I play, I will pay this amount of money given by f. F is defined inside my set omega, and it's a continuous function inside. I pay epsilon squared, so a tiny amount of money, but I will pay this tiny amount of money a lot of times because I'm going to move inside my domain many times until I exit. Okay, the game continues. You start with the first position, you make one step, you get x1, then you choose a possible different orthonormal basis and a possible different set of coefficients. You restart again, you get x2, etc. And you define the exit time, the stopping time for the game is going to be the first time when you exit the domain. So when I exit the screen, the game ends, and I will get some amount of money given by g, by this little g of the final position. So those are the rules of the game. You can move at random, but choosing the directions where you point, and chooses some coefficient that give you the length of the possible movement in the 2 directions that you move. And you are going to do it until you exit the screen. And when you exit the screen, you will get this amount of money. You will get the final payoff. g of x tau plus minus, sorry, this is with a plus because the player gets its amount of money, and with a minus, the running payoff epsilon square f, because this is what you are paying. You are paying 1/2 epsilon square 1 of f of 1 over n, and you are summing all the running payoff along your positions, and the final, you add the final payoff. This is what you get in one of these movements of the game. Of course, everything is random here. The terminal time, the stopping time in which you finish your game is a random variable. And also the xj, the positions of the game are random because you can choose the directions, but the next position of the game is selected randomly with the same probability among all possible choices that you make. Okay, what is a strategy now? Now the game has something because you can decide at every point what are the orthonormal bases and the multiples, the coefficients that you are taking to move. So a strategy for the player is the choice of the orthonormal basis and the number and the coefficient at every possible point, at every possible play inside your set. So you start, you choose some basis, you move one step, and then you can choose another basis with a different set of coefficients, and then you continue, and this is a strategy for the player. Okay, given a strategy, if you fix a strategy, so you assume that you are going to play exactly with the same basis and with coefficients equal to 1, you can take all the coefficients equal to 1, for example. This is a possible choice because the product of all the coefficients equal to 1 is equal to 1, and they are all less than 1 over epsilon, or epsilon is small enough. So you choose this thing, and you can choose this for every possible point inside your domain. You take this strategy, you fix this strategy, and you can compute the expected, because now everything is random but depends on the coin tosses. So you can compute the expected amount of money that you are going to get at the end. This is the expected total payoff of the game. This is minus the running payoff, and you have the final payoff, but you compute the expected amount of money that you're going to get, starting at X naught, playing with this strategy. Okay, now assume that the player, the controller that you have in your game, wants to minimize the payment, and you define this value of the game. What is the value of the game? The right value of the game is the infimum among all possible strategies. Now you are changing among all possible strategies that the player can make. So every possible choice of any orthonormal basis and any set of coefficients among this set of coefficients I n epsilon of the expected value. And what is this? What is this value of the game? This value of the game is the best possible amount of money that the player can hope to get playing his best. Because the best thing that you can do is compute the infimum. Of course, this infimum, it is not said that it is attained, so you don't have necessarily an optimal strategy for this game. This is an infimum, and nobody claims that this is a minimum, in fact. So there's, in general, I don't know how to prove that there is an optimal strategy for the player. Okay, what is this this mean value? This value, because this is a sort of mean value because we are computing some expectation in here. What is this U epsilon has to do with the previous thing and with Monge-Ampère equation? Okay, this U epsilon verifies a formula that is called the dynamic programming principle for the game in the literature of game theory, and it's the following thing: U epsilon, so the expected amount of money that the player hopes to obtain if he plays his best at some point X, is the infimum among all possible choices of the orthonormal basis and the infimum among all possible choices of the coefficients of what he will get, provided that he made one step. And all the possible steps that he is going to make are encoded in this x plus or minus epsilon, the square root of the coefficients in the direction of the vector vi, and you're computing 1 over 2n. This is 1 over 2n, 1 over n plus times 2. This is 1 over 2n. So this is the probability of making each of these steps. And you subtract, of course, you are taking the payoff. At this point, you expect to have this amount of money minus the thing that you have paid at this point. And of course, for points that are outside omega, the game ends instantaneously, because when you are outside, you stop the game, you stop everything, and you get the amount of money given by G. So you are not playing, you don't have any running payoff, you don't have any choice to make, but you are getting G of X. So you have an exterior data given by G and an equation inside omega for points that are inside the domain that gives you the mean value property with this f of x epsilon square, but without the little law of epsilon square. And if you remember, let me recall you what was this one. This one was the mean value property that holds for Monge-Ampère equations, but with the little law with the error. Now we are saying that the value of the game, this expected amount of money that is the best thing that the player can hope to achieve, verified exactly the same formula, but without the little law of epsilon square. So you have that the mean value formula is the equation, the mean value formula without the error term gives you the equation that is verified by the value of the game. So the value of the game u epsilon, when you put u epsilon here, u epsilon there, verifies this formula point-wise. And you have to prove that this is indeed the case. Here you use probability ingredients, because this is a probabilistic way of defining the value of the game, but here you have an equation, like a PDE. This is not a PDE because you don't have derivative, but it's sort of a discretization of the Monge-Ampère equation, a discretization of the PDE. And you have to prove a little more than that. That is the equation that characterizes the value of the game, in the sense that you have uniqueness for solutions to this dynamic programming principle inside your domain with exterior data equal to G. Okay, now the last result says this value for the games converges uniformly inside omega to a continuous function. So the limit is going to be continuous. And the limit is the unique viscosity solution to the Monge-Ampère equation inside omega. This is not surprising, because this formula that verifies the u epsilon is the same formula, the same asymptotic mean value formula, except that you don't have the little law of epsilon square here. So this is okay, this is expected in some sense, with boundary values equal to G. And one remark is that we asked for the domain to be strictly convex here, and something that we don't know, but I think that it is worth thinking about it, is what happens with the values of the game when the domain is not strictly convex. And when the domain is not strictly convex, you will not have a solution that is a viscosity solution to this problem that is continuous up to the boundary. So probably the boundary data is lost in this case, but can you prove convergence of the values of the game even if the domain is not strictly convex? And this is something that unfortunately I don't know. Okay, so one extra, I have two extra slides. The first one is that what is the general picture that we are looking at? You have that three things are equivalent, in the sense that you have a mean value property, an asymptotic mean value property that can be continuous, integrating in the whole ball, or discrete, integrating in directions. You also have a dynamic programming principle, that is the formula that is verified here by the values of some game. And you have a PDE. And the PDE is usually like a Monge-Ampère equation, a local PDE. And what is the theorem that is behind? The theorem that is behind that holds for Monge-Ampère, holds for the Laplacian, holds for the P-Laplacian, holds for Pucci operator as well, is that if you have a real function, it verifies an asymptotic mean value formula. It also is a solution to a PDE that could be nonlinear, like Monge-Ampère. And the function can be also approximated by some value functions on some games that are solutions to a dynamic programming principle. So you have the second statement is you have a game theoretic interpretation or a game theoretic approximation of your solutions. The third statement is the function is a solution to a PDE, so you have a PDE behind. And the first statement is the title of the talk. You have a mean value formula for the equation that is usually nonlinear as well, and is in an asymptotic sense. And all these three things holds for the function u, always in the viscosity sense. So u is a solution to the PDE in the viscosity sense, verifies the mean value property in the viscosity sense, the asymptotic mean value property in the viscosity sense, and is the limit, u is the limit of these functions u epsilon, as epsilon goes to 0, the values of the game. Okay, this approach is very flexible in the sense that you can do it in the Euclidean space, but you can also do it in the Riemannian manifold. You can do it, let me say, in every space where you have a distance, because you want to define the ball of radius epsilon, and you need a measure to compute the mean values, the integrals. In there, it also happens in sub-Riemannian manifolds, so you can also do this for the Heisenberg group. You can also do this in discrete settings, in discrete ambient spaces like graphs or trees that are infinite graphs. But what are the constraints of this approach? This approach is general. You can do it for several, let me say, several ambient spaces, but you need real value functions because we are using viscosity theory, and only second order PDE for which a maximum principle applies. So you need some ellipticity behind all these things. You need some monotonicity of the operator of the PDE in the Hessian in order for this to work. Okay, so three references. The last one is the paper that contains the results that I talk about. Except for the game, the results concerning the game are not contained here, and we are writing something about this. And the first two references are two books concerning this general game theory and partial differential equations approach. So the first one is with Pablo Blanc, the same co-author of this work, and the second book is by Marta Lewica, also from Pittsburgh University. And that's it. So many thanks for your attention, and muito obrigado pela atenção. Sorry about my Portuguese. My Portuguese, I learned some Portuguese in Brazil when I traveled to Brazil, and my Portuguese is a disaster. So
Perfecto, Julio. Gracias. So let's thank